We were really excited to have Richard here. So initially the plan was that I would present how to use 2DX image on Wednesday. I don't know of any lab that does work on membrane proteins with 2D crystals and has not at least downloaded 2DX image. So I think there should be interest in how to use it. And then Richard agreed to come. And we were so excited that we said, great, he has to have a lot of space and time. And we had a wonderful talk by Richard, and then we forgot to put the talk about 2DX image back in. And so today we have 45 minutes IPLT, diffraction processing, which is important and great, and another 45 minutes about diffraction merging in IPLT, which is also great, and then 30 minutes about 2DX, and that's all we have in the whole workshop, except the introductions on Monday. And in addition, we are already at lunchtime. So, and there's just almost nothing about it. So my proposition is to have a session about 2DX image that I could give tomorrow instead of swimming in the Rhine because it's raining anyway. And we can vote tomorrow morning or after my talk if you want to hear another 45 minutes of me speaking about something that's, so instead of visiting Basel. So tomorrow we have another 45 minutes possibility here. There's this free time, and we could move this a bit further down. But we can vote about this tomorrow morning and see who's still there and so on. So, and in a way that's also good. I think the talks we heard right now from Per and from Anshi, for example, and from Richard, they explained how to use the MRC software and how to do the unbanding. And 2DX runs that with the same programs and the same variables. So tomorrow we will hear a talk by Xiangyang Zhang about her work on a single particle approach to 2D crystals, and that addresses the case when your crystals aren't well enough ordered that you can do unbanding or electron diffraction. And in some cases, hopefully always, the maximum likelihood single particle approach may be as good as the unbanding approach. And then I will also explain the work that Brian Gibson did at the end, in the last half year of his PhD on projective constraint optimization, where he exploited the oversampling that we have at low tilt angles. So he recorded many images at low tilt angles, 0 to 20 degree tilt or so, and you have many of them, hundreds. And so every Fourier pixel at the beginning of your lattice line is sampled many times and precisely determined. And you can use that to predict what you have along your lattice lines further up, even in the missing cone. And that resulted not only in an improvement in so not only in full reconstruction of the data in the missing cone, but the final reconstruction that he had a much better vertical resolution than X and Y. So he transformed the problem of the missing cone into a better Z resolution than X and Y. And I will present tomorrow how he did that. It involves that he puts away with sinc interpolations. He uses more complicated functions, and he doesn't use Fourier transformations anymore. He uses a matrix algebra. And today, in the next 20 minutes or so, I want to show you how you can use the 2DX package to do the merging in 3D. We developed 2DX to help you with the management of your project. It's a kind of LIMS system or so for your electron crystallography project. Its function is also to guide the users which MRC program you should use in which order and what do you have to look out for. Some of the results are labeled as important and others are labeled as less important, with colors, for example, red and black. We wanted to provide a user-friendly tool to use the MRC programs manually or automatically or semi-automatically. And it ended up with this software that we can use to use the MRC and CCP4 programs, but also to use Xiangyang's maximum likelihood software. We use Spider at one point and call Chimera, and we are discussing at the moment how to merge this with IPLT. We don't know yet under which platform and under which umbrella, but somehow I think what is available in the different packages for electron crystallography should be brought into one user-friendly and high throughput and mathematically performing package, including what has been developed in IPLT, so that we collect all the goodies and put it in one thing. So to make matters worse, I have little time left and I don't have any slides. So here you need many photos because it's a movie, it keeps going. So, so maybe so what else do I want to show you? Okay, so the merging process takes you through different steps. Anshi explained that, and Pia a bit. And you have lots of different files and programs that take you from one file to the next one. You have your evaluated amplitudes and phases with CTF or TTF refine or correction in there. You merge them together into one big file. You average equal values together and transform that with an CCP4 program into a 3D map in the end. And for all these, you have different file formats. And these files, most of them are text files, ASCII files. Once you are in the MTZ format, it's a binary format, and you're dealing with floating point values. But here it's ASCII files, and there is the trap that if you write the ASCII files out as a text, and you use sometimes 8-bit and sometimes 16-bit scanner and maybe others, floating point values, you have to watch out what kind of number you put down for the amplitude. And if the number has only one digit left, 0.1 or 0.9, then you lose precision here. And if the numbers are longer than the digits you have, then you may just mess this up and suddenly the amplitude writes into the K vector and your programs crash. And so you have to look through these file formats, and it gets pretty confusing, I find, what program calls which and in which order. And so we tried to collect this information into a workflow, and we have this on this website. And the website, 2dx.org, where you can download this 2dx software, has, among other things, so here down here is, for example, from 2006, the movie where we filmed Gyobu, how he makes the sandwich. And he annotated that and corrected our annotations. Here you have the data flow. And the data flow section are pages where we take a data set processing with examples through one image or merging in 2 dimensions or merging in 3 dimensions. And if we go into the merging in 3D, which today we speak about, then we have here examples of which program is called in which order, so one program after the other, and then what it uses as input variables or input files, and then examples of these files, how they should look like, and explanations of what these columns are. So this is H and K, and then the star, and amplitude and phase, and the amplitude is the original amplitude, not yet CTF corrected, but the phase is here correct, CTF corrected, at least phase flipped, and so on. And it's defined here what is where, and from which micrograph it comes, and it takes you from one program to the next one through all these different steps with examples. And you can then look on your hard drive which program you call in which series. If you use the MRC programs, you would do this in shell scripts or manually. And if you use 2DX, then it runs behind the 2DX also, but it still uses the same programs and the same file formats. And you can, in the case of 2DX, just double-click on the file name and open it and check if this looks the way you're expecting it. Yeah, and if, as Anji said, if you have in the lattice line some outliers, you can then go in and say, okay, I have at a certain Z position, at a certain lattice line, a problem, and you can try to find where this problem starts to occur, from which image it comes, and try to trace things backwards. So on 2dx.org, we have this workflow file system here with examples. And then this is our software, 2dx Merge. And the purpose today, what I want to show is how to use this for merging. Behind, we run the pure MRC software. And in the merging step, we modified very little. Mostly only cosmetic to get the out file into the log, the output into the log file window, and the images that are produced show up here. You can always double-click these things, and if variables are determined, then they show up here and go back into the database. The result things that show up here, they can be images, and if you double-click them, you open them in the full-screen browser. They can be amplitude and phases. They are opened as a text file. They can be MTZ files, and if you double-click them, we transform them into an ASCII file, which is displayed then as a text to you. So you can also directly look at MPZ files and PostScript files and 3D volumes and so on. 3D volumes are opened with Chimera by default. Here is a kind of Excel sheet-like table where you have for every image that you have in your project, you have a line. And so those are the file names or directory names, and here are the phase residuals and phase origins that are currently there, and the tilt axis and tilt angle values. And we group them together by tilt range. So this is non-tilted, 30-degree tilted, and 45-degree tilted. So I have 6 tilted and 3 non-tilted images here. And then you can step over these by just clicking on them or stepping over them, and you see here this preview. This is correctly centered. It's a P4 crystal, and this one is not correctly centered. It's here, and this one is also not correctly centered. It's there. And now the process here should be to center this correct, so to align them. And you would do this so that you first select only one that happens to be correct, and you can do this manually. By the way, if you double-click this, then you open 2DX image with this image. And this is what I can explain tomorrow again, and in the practicals, how to process an image. It goes over the unbanding that we discussed and over CTS correction, and the last script would be generate a map. Then you have your map here. So, and this is the map that you see here. And now the other 2 images are not correctly aligned to this. And what I do is I run the script merge once, which means I take the one selected image and run a couple of scripts, among them oric tilts, and produce a merged amplitude and phase file, which is somewhere here. Are we in 2D mode or in 3D mode? This should be the 2D mode. Okay, we're in 2D mode, yeah. So, and then we have our merged data set, which is here an amplitude and phase file. And if you want to look what all these columns are, that's on the web page. So merge APH. We use oric tilt, and oric tilt is a complicated program. There's a lot of it in it, beam tilt refinement, for example. What we do is we create, with all the parameters that we have, a C shell script here that calls oric tilt and then runs it, and the output of the oric tilt run of this entire script goes into this other log file, text file here. And so by double-clicking here, you can see what kind of script 2DX Merge made for you, and it's made from the database. And then when it runs, it produces a log file, which you can double-click here and then check, as Pierre explained, everything that you want to see. Now we have a reference, which is an APH file. And now we want to take the next script and say, now we take these 2 images and align them onto the reference. And for that, we need a search range. So we are aligning this, in this case, with 61 steps of 6-degree step size. So we are searching the entire unit cell. And what these are is something I don't have the time to explain now. But you would take these other 2 images and align them to the first one. And now the phase origin values for these 2 images here have changed by these values, by 90 degrees and 45 degrees, 54, and 72 and 84. So they changed, these 2. And now hopefully these 2 are aligned to the first one, the reference. So I can regenerate these projection maps to check what we have. So this was correct in the beginning, and now these other 2 are also roughly correct. Not very precise, but okay. And now we can do this a few more times. This is the number 2 here. The screen is not large enough. If I click this now, what this does is it takes these 3 images, merges them together, and refines the phase origins to the merged average, and then does this a few times. You can set the counter here to 20 or 10 or what you want. Now we are done, and you can do it one more final time, the merge, and then generate the map. We are still in 2D modus, and the final map now is the averaged map from the 3 pictures that we had here. That's 2-dimensional. If you go to Fourier space, what we have here is this case. We have non-tilted images. So in 3D Fourier space, we have now defined the variables just along this one non-tilted plane. And now we have tilted pictures in addition, and their Fourier transformations correspond to a tilted section, and we want to merge those to our two-dimensional data set, and as Anchi explained, now we have this problem that in a very thin two-dimensional data set, we can't really have enough overlap to align a tilted plane. And there's this Z star range variable which we have to put to a large value so that also a tilted plane along a lattice line up here still finds some reference point down there, even though it's not exactly correct, but it's better than not having anything at all. That's one of the Z star range is one of the sensitive MRC parameters here. So in order to switch this to 3D mode, I put this to 3D. And then we have now a merged data set here. I don't use the non-tilted, and I use the 30-degree tilted pictures. And I think my Z-star range is still, where's this? So my Z-star range is still at a large value, 0.5. That's large enough. Yeah. This is the Z-star window. Okay, if I now run this, what happens is that it takes our two-dimensional merged data set that we have, and it takes these 30-degree tilted images and refines their phase origins against our 2D reference. So, and that's it. And their phase origins have changed shockingly little. So who knows what happened here? Were they? Okay, so you can check that soon. So what happened here is that by clicking that button, the C-shell script was generated with lots of variables that call 1, 2, 3 rounds of auric tilt to run over these 3 tilted images. And all these entries come from the database of these 3 pictures. And the C-shell script was then launched. You saw the progress bar run. And in the end, you get this log file. You can see what auric tilt did. And here's the log file. And then you would have to speak with the experts like Anchi or Peer to see what this all is. And you see that it went over all these pictures. This is one picture here, and this is the phase origin that it started with. And then it does all kinds of comparisons, in this case down to 7 angstrom resolution. And you can see here how many reflections in that resolution range were actually found for comparison. And those were enough. And this is the cross-correlation map. And there happens to be a peak, which is roughly centered, so that's good. And the new phase origin was calculated by auric tilt. And our additions to this program is that this is not only in the log file, but also modified so that it goes back into the database. And this happens for the first, for the second, and for the third picture. Each of them has a peak somewhere in the cross-correlation map. And there is a sufficient number of spots that was used for this alignment. So now we have merged these in there. Maybe I look at these, I regenerate these maps, and so we can look at the freshly made phase residuals, and they are correctly centered roughly. And now we merge them all together here. So now we have a reference that is slightly three-dimensional because it has the 30-degree tilt pictures in there. And I can do this in a few iterations. So merge it together and refine the pictures, and merge it and refine it. And the more pictures you have and the finer steps you do, only fine alignment at the end of the phase origins, the more iterations make sense. So up to 10 or 20 or so. Then it is longer than the time we have here. So now we have a 3D reference, and so then we don't use these, but then take the 45-degree tilted pictures and align them onto our reference. So you go step by step. Already? Okay. And then you can take all of them together, so also 30-degree and 0-degree, and do this in a few rounds. So this is 2 rounds here. And you can see the phase origins move or not. So there was still one change of 60 degrees. We are still in 6-degree step size. And when these all go to small values, then they're all down to 0, then nothing changes anymore. You regenerate your maps. You do a final merge, and or maybe we look at the maps. So they are all correctly centered, yeah, roughly. So we also have here the protein album where you see all these maps in one overview, and you can look through these and see the taxa tilt axis displayed there. So, okay. So then, if we are happy with this, we generate a 3D map. We are in 3D mode, so this time it doesn't only make a 2D APH file, but it also makes a volume, and it uses CCB4 for that. Where is my volume? Should be there in a second. So this is the two-dimensional result, and the 3D, I don't know why it's so slow. So there is the 3D volume. And if I double-click that, I open it in Chimera. So now this little computer is supposed to open Chimera. So and this is 6 tilted pictures, and it's not great, but it's technically working. Yeah. So now we have this 3D thing, and we have an MPZ file, and now we can go back to these pictures, for example, this one here, and reprocess them with MakeTran. So I open this by double-clicking this, and then we open it in 2DX image, and the usual scripts here run unbending in 1 and 2 and further iterations. But you can switch this over and say, I don't want to use as a reference the Fourier filter picture itself. I want to use our 3D merged data set, and I switch this to synthetical reference. And now if I run this synthetic unbending script, it takes a while. I don't have the time to run it here. And there are some other parameters for it to do it. But what it does is it creates these synthetical references. I double-click it, so I open it in the full-screen browser, and I display it with phases because it's beautiful. And so this is what the color is, the phase, right? Here in this, and this is the Fourier space with synthetically placed amplitudes and phases. That's Edmund Kunjit's program from the MRC package, and this is calculated. And these things are Gaussian blobs of a certain diameter, which is one of the parameters for MakeTran. And the smaller they are, it corresponds to the larger reference. And so you make this, and this is then the perfect reference for unbending. And we even make 2 of them with 2 different diameters. The first one has a small diameter, and the other one has a larger diameter. And so these are now larger than before. So we have 2 for because the first one corresponds to a large reference of 7 by 7 unit cells, and the second one corresponds to a smaller reference of 4 by 4 unit cells. And we do this because we run 2 searches of quad search. The first one determines the rough lattice distortions, and the second one refines that error profile with a smaller reference, allowing only small deviations. And so if you run this, you generally improve the resolution, as Angie explained. I have also a slide here. This would be for non-tilted pictures, the approach where you are in CTF affected space in this area here. This is more or less the slide that Richard Henderson and Pierre and Angie showed about the workflow in the MRC programs, where you do the reference creation and the unbending, and then you evaluate, and you correct the CTF on the evaluated data. And when you have a merged data set, you can use MakeTran to produce your perfect reference. And in this case, you apply the defocus, so the perfect reference has a tone ring, as we have seen it. And this is then much better as a reference than the Fourier filtered reference here. And when you have a tilted picture, you can use it this way, that you first use TST mask to convolute each Fourier spot with a split spot profile to get rid of the CTF effect. And from then on, you're CTF free, and the unbending is done after the CTF correction. And here you have the TT box program to evaluate amplitudes and phases under consideration of the TT transfer function. No CTF correction anymore. And when you merge these together and then want to make a synthetic reference, you have to make this CTF free. So this here should be a make-tran run without any defocus. So if you set the defocus to 0, then no CTF correction is applied, but the contrast then is inverted, so you have to invert it again to make sure that you have the right color of your reference, but that's all implemented. And so this would be the synthetic reference creation with make-tran in the case of tilted pictures. So, and then that's how we would do this in this program here. As also with 2DX image, all these parameters here, they have on the right mouse click the help function, where you see some short explanation and examples about these parameters. And when you click on this, you are thrown onto the web page where you have longer texts. And if something is wrong or missing there, you can leave comments, and many people have done that. So I think that's it for today. Here's a maximum likelihood script, and this will use all selected images, tilted and non-tilted, for a 3D maximum likelihood run. Xiangyang is working on that. That's a prototype software here. And we have a better, more reliably working two-dimensional version of this here for non-tilted, or for non-tilted single pictures, where only the one picture that is processed with 2DX image in this program is used for the maximum likelihood run. And this runs fairly well once you have set these parameters correctly. Okay, so now I think it's lunchtime. No, are there questions? I'm done anyway.